Reactivity of neutrinos in superconductive ion ring arrays. The core propulsion mechanism of the gyroscopic drive relies on a radical approach to neutrino reactivity. Under normal circumstances, neutrinos interact so weakly with matter that trillions pass through entire planets unimpeded. However, when structured within a superconductive ion ring array, where superconducting materials generate ultra-stable, high-energy electromagnetic fields, the probability of neutrino interaction can be subtly amplified through phase locking and magnetic field manipulation. Superconductive ion rings, enhancing neutrino coupling. Each ion ring within the gyroscopic system is composed of ultra-cooled, zero-resistance superconductive material. Charged ions are suspended and accelerated within the ring structure, generating a persistent and stable plasma envelope. This creates a dynamic magneto-electrostatic torus which, when spun at relativistic speeds, subtly distorts the local vacuum structure. This distortion forms a lattice, a sort of quantum sieve, that statistically increases the probability of momentary neutrino capture or deflection via magnetic resonance. While the individual neutrino interactions remain minuscule, their collective influence across multiple rings becomes measurable when arrayed in precision-aligned configurations. By constructing arrays of these rings in dual-row configurations, their individual neutrino-affecting fields are overlapped and synchronized. When phased correctly, they produce a collimated beam of modulated neutrino flow, redirected through constructive interference. Two such beams, emitted from opposite rows, are directed to intersect at a focal point ahead of the spacecraft. The intersection is not a collision in the traditional sense, but a standing wave interference zone where phased neutrino density reaches a localized maximum. At this focal point, the interference pattern created by the phased neutrino streams imprints a structured distortion into local spacetime, a synthetic gravity well. Unlike a natural gravitational field formed by mass, this one is dynamically generated and sustained by the spinning superconductive gyroscopes. The intensity and shape of the gravity well are determined by the rotational speed and phase coherence of the superconductive rings. Faster spin induces greater kinetic energy, which in turn amplifies the neutrino interaction envelope and deepens the resulting gravity gradient. This synthetic gravity well creates a space-time slope, a directional flow that the spacecraft is pulled into. It mimics the effects of gravitational acceleration without requiring traditional thrust or expelling mass. The ship effectively surfs down a space-time curvature of its own making. The feedback of these interference patterns upon the surrounding vacuum not only shapes the gravity well, but stabilizes it. This imprint forms a localized space-time distortion zone where motion becomes not just possible, but energetically efficient. The ship essentially rides its own wake, guiding itself through the cosmos by continually reshaping the gravity focal point just ahead of its path. When dual neutrino beams are phased and projected from the synchronized superconductive gyro arrays, they intersect at a constructive interference point ahead of the spacecraft. This intersection forms an energetic interference cavity, a localized region in spacetime where high-density neutrino waveforms imprint structural tension into the quantum vacuum. This cavity acts as a synthetic gravitational indentation, or a gravity well, into which the spacecraft is continuously pulled. The shape, depth, and orientation of this cavity dictate the direction and intensity of propulsion. The interference cavity is not a simple point but a three-dimensional ellipsoid or torus variant, shaped by the phase differential, beam angle, and wave harmonic interaction. Cavity characteristics. Parameter effect on cavity beam convergence angle theta determines cavity orientation and elongation phase offset dph. Shapes curvature symmetry frequency stack phi, controls wall sharpness and edge falloff ring velocity v, affects depth and strength. External neutrino flux psi, alters cavity compression profile. At optimal alignment, the cavity forms a forward-biased oblate ellipsoid with the ship positioned behind the narrower end. At minor phase variance, the cavity deforms laterally. This distortion is key for steering. To steer at or near light speed, the phase-locked oscillator grid or PLOG introduces minute phase delays between the left and right gyroscopic arrays. This phase skewing alters the angle of constructive interference, shifting the cavity's centroid off the direct longitudinal axis. The ship, always falling toward the cavity's center, naturally adjusts course to remain aligned with it. Lateral steering example, phase offset, 0.002 radians left side delay. Result, beam convergence angle biases right. Outcome, gravity well pulls ship gently into rightward arc. This allows for non-inertial vectoring, true steering without physical thrusters, using pure space-time gradient manipulation. When near planetary bodies or moons, gravitational influences are factored into cavity shaping to bank the synthetic well. This enables gravity-assisted turns without traditional gravity slingshot mechanics. Alright, let's go through the procedure. First, read the planetary vector field via NST. Then, offset the neutrino beam focal zone by plus 1.3 degrees on the approach side. Finally, increase the frequency stack density to deepen the cavity edge nearest the gravity source. The ship will follow a curved space-time path with a stabilized trajectory. Now let's talk about the cavity shape modes, or CSMs. CSM-1 is a symmetric ellipsoid used for standard forward pull. CSM-2 is a lateral asymmetric shape which is useful for steering via lateral skew. CSM-3 is a compressed torus ideal for tight turns or course reversal, often referred to as drift. CSM-4 is a split bias node, allowing for multi-vectored navigation near stellar bodies. Finally, CSM-5 is a hollow core shell, which is employed for emergency inertia dump, also known as gravity bleed. At relativistic speeds, even nanosecond desyncs can destabilize the cavity. The cavity's spatial pressure, measured in quantum stress units, QSU, must remain within the following envelope. Stable steering QSU range, 4.8 times 10 to the negative 11, is less than or equal to QSU, and less than or equal to 6.5 times 10 to the negative 9. Below range cavity collapses, inertial lock lost. Above range field ripples, potential decoherence hazard. The BPCE auto-adjusts focal length to stabilize cavity depth dynamically, using neutrino telemetry to predict and compensate for cosmic ray or particle cloud interference. Imagine a spacecraft riding a tunnel carved into space-time. The tunnel is made of synchronized neutrino compression patterns, continuously reforms just ahead of the ship, can lean, curve, or spiral depending on phase input, and reacts instantly to phase signal updates from onboard AI. This system allows seamless, thrusterless course correction even at relativistic velocities. Gyroscopic drive, the neutrino engine for inertial spaceflight. The dream of reactionless propulsion has captivated scientists and engineers for decades. Historically, propulsion systems have relied on reaction mass to move through space. This reliance presents a significant problem for long-distance space travel. But, with the advent of the gyroscopic revolution, we might be on the brink of a breakthrough. Let's delve into the physics of motion and inertia. Newton's laws have served us well on Earth, but they do have limitations when applied to the vastness of space. Centripetal force and gyroscopic precession offer intriguing possibilities. Understanding inertial frames and relativistic effects is crucial for advancing our propulsion technologies. Now, let's talk about neutrinos, often referred to as ghost particles. These particles have unique properties that make them fascinating. They're incredibly hard to detect, yet they are everywhere. The idea of interacting with neutrinos for propulsion could revolutionize space travel as we know it. Chapter 3. Superconductivity as the key. Superconductors and zero resistance, well, they go hand in hand. When we talk about magnetic flux trapping and the Meissner effect, it gets really fascinating. Imagine creating gyroscopes that don't lose energy. That's the magic of superconductivity. Chapter 4. Dual row configuration. Why 2? Synchronization and phase offset are crucial here. By manipulating torque via dual-axis control, we can achieve remarkable precision. And of course, how to balance opposing forces for motion is an essential aspect of this design. Chapter 5. Constructing the neutrino interactive gyroscope. First, we start with material selection, superconductive alloys, ceramics, and so on. Then we focus on magnetic field shaping and containment. Finally, layering with neutrino interactive plasma sheaths completes the process. It's quite the intricate construction. Chapter 6: Inducing G-force motion. Now let's dive into how spinning massive superconductive gyros can create an inertial push. By using neutrino interaction as a pseudo-reaction mass, we can achieve this effect. Additionally, controlling acceleration and inertial damping plays a crucial role in this process. Chapter 7: Navigating with the gyro drive. Vector control through precise rotation, stability algorithms and real-time adjustments. The concept of inertial surfing through space-time. Chapter 8: Real-world applications and implications. Deep space exploration, interplanetary travel without fuel. Emergency escape systems and station keeping. Chapter 9: Theoretical challenges and skepticism. Current limits of neutrino detection and interaction. Energy requirements versus output. Possible breakthroughs in material science or quantum fields. Chapter 10: The future of inertial propulsion. Integration with AI navigation systems, pairing with warp bubble or Alcubierre concepts. Humanity's next leap in space civilization.